Welcome to Functional Programming. I'll be your host, Kyle Corley. And see, by the end of this lesson, I want each and every one of you to be able to recall at least 3 principles of functional programming. And if we get that far, I'll call it a win. Might do some extra stuff also. So to start with, I'm going to give you a couple minutes. I want you to research some principles of functional programming. So don't get too far into what they are just yet. We're gonna do another round where we dig into each one of them a little bit. But let's see if we can get a good list going. So I'm going to give you 3 minutes. See if you can put together as many principles of functional programming as you can. Go.
I just have to say that I did not see Lynn's background this morning because she, I think, was on a different page, and you just popped up in speaker view, and you are in grave danger. I just
Yeah, I got a problem. But you know what? At least I won't be on the toilet when I go.
You've got a good outlook right there.
Let's call back. Spoiler alert.
I regret to inform you all that the actor who played that guy, that was his big moment. He's the guy who got eaten on the toilet, and that's it.
Well, he's remembered for something.
He went on to be in an Air Bud sequel. It's just not great.
Speaking of which, I don't know if any of you ever watched any of the Beethovens after the first one. That series flew off the rails. I watched one with my kids the other day. It was Beethoven's 7th or something. And now Beethoven has magical powers, can talk, and is world famous.
Good dog.
Wow. I don't think I ever made it past the first one, and I think it sounds like I'm not worse off for that.
Yeah.
Accurate. All right, so let's make a list. Lynn, give me 1 principle of functional programming.
It uses pure functions where application state flows through the functions rather than being passed down.
Beautiful. Derek, give me another principle of functional programming.
Referential transparency.
Thank you. Very good. Michael Navoy, what you got?
Immutability.
Love it. Ben Dunn, give me another one.
Uses a disciplined state.
Yep.
I don't know nothing about that.
Sam Evans, give me another one.
Functions are first class.
Damn it, Sam, you took mine.
Gordo, what you got?
Higher order functions.
Beautiful. Haley, what you got?
Declarative approach.
Excellent. B-Rad, anything that's not on this list already? Unmute.
Modularity. Has that been listed or no?
Nope. Love it. Brooke, do you have one that's not on this list? Okay. Matt Long, you got one that's not on this list.
Is recursion separate from what we've talked about so far?
Yes, it is.
Okay.
Let's see. Christine, you got anything that's not on the list?
Is type systems more related to declarative approach, or is that separate?
I call that separate.
Okay.
All right. So it's a pretty good list here. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Ah, Kismet. All right. So I'm going to assign people some topics, and you're going to research them. So I'm going to say, let's do this backwards. Christine, why don't you teach us about pure functions? Matt Long, your referential transparency. Brooke, you're going to be immutability. B-Rad, you're going to be disciplined state. Haley, you're going to be first class functions. Gordo, you're going to be higher order functions. Sam, you're going to be declarative approach. Ben, you're going to be modularity. Mr. Navoy. You're going to have recursion. Derek, you're going to have type systems. And Lynn, why don't you do pure functions also? All right, so I'm going to give you 10 minutes. I want you to dive deep on whatever your topic is and be prepared to share highlights, your takeaways from each of these. Go. Another 30 seconds. All right, time's up. Let's share a little bit. So let's start with pure functions, and I want to hear from Lynn first. So Lynn, what on earth did you find out about pure functions?
They are independent. So that means that they produce no side effects and they are easy to move, refactor, and reorganize. They are also immune to bugs that can happen when you have shared mutable state. Given the same input, they will always return the same output. And basically what it boils down to is if it makes sense to call the function for a purpose other than using its return value, it's not a pure function.
Oh, beautiful. Very well put. Christine, do you have anything to add to that?
I think the only thing is that pure functions are referentially transparent. Yeah.
Okay, very nice. Outstanding description. Good job, everybody.
Quick question.
Yeah.
Same input, same output. There's a word for that, isn't there?
There is. Anybody know it? Starts with an I.
Immutability.
I mean, when you...
Idempotent.
That's not a word.
I was just thinking when you did ID, I was like, you misspelled that, man.
That sounds vaguely obscene.
A function that always generates the same output when given the same input is idempotent. You think of a function that doesn't necessarily rely on any outside state, doesn't have any side effects, but still isn't idempotent, doesn't generate the same output every time. There's two things in particular that are really common that screw with something's idempotence and thus its purity. Anything that has to do with randomness, anything that has to do with the current date. Those are the two situations that you will run into that will screw up the purity of your function. Because if it's dealing with the current date and I call that function tomorrow, I could have given it the same inputs, I'll get a different output. If it's using a random number generator, no bueno. Now the random number generator, and actually for that matter, the date, we have ways around both of those. Can you think of a way that we can make something that uses random numbers return the same output every time? It's also useful for testing.
Maybe this is cheesy, but could you just make the numbers strings?
No.
And it's always returning a string.
The trick has that acronym.
You pass the random number as an argument into your function.
So that's how we would do it with the date. The way you get around that is that you have something else generate the date and then you pass that in. You can also do that with the number, but if the whole point of the function is to generate the random number, we still have a way we can get around that. Anybody know what PRNG stands for?
I know RNG is random number generator.
Cool. All you got to do is add the P.
P random number generator.
Pseudo?
Pseudo.
Pseudo.
Oh, I heard it. Who said it?
Here?
Nope, not pure. Pseudo. Pseudo random number generator.
That's cheating.
Random number generators are not actually random. Like they go off of formulas and stuff because they're computers. It's beeps and boops. The computer doesn't know how to be random. So what it does instead is it does things that are pretty damn random. But what they work off of is seed values. So you go, all right, given this seed, I always get the same sequence. And then you just make atmospheric noise, something else, generate that initial seed value. This is how random numbers in computers universally work.
I think that's how we got random polls for the tarot app we made.
There you go.
I think we like stumbled backward into this concept.
Yes. If you've ever done a video game, like a roguelike or something, and they give you your seed value, or you've done a randomizer for a video game before, it's like, oh, you got to check out this one seed. Those are just starting places for the random number generator. So if you pass in a seed, you should be able to get the exact same output every time.
Minecraft.
A little bit of a tangent, but back to pure functions. This stuff is super easy to move, refactor, organize. It's also easy to test. If something produces the exact same output every time, way easier to test that. Cool. Matt Long, tell us about referential transparency.
So what I got on referential transparency seems to be building on or very directly connected to pure functions and idempotency. Basically, if something's referentially transparent, it has to be a pure function. And it basically means that you could replace that function with its value without impacting the program. So the way I'm trying to kind of mentally process it is like if you had a function that is adding up prices for items, you could take that and replace it with the total price and it wouldn't affect the program. But if you put a global variable inside that function that would be altered by what your function is doing, then you're altering the program. You can't replace it by just a value, and then it can't be referentially transparent.
Preach, Matt. You got it. So in practice, this looks like this. If I had a function that just returns the number 4, that is interchangeable with the number 4. So like, let's see, what are some operations that I can do with numbers? 24 dot to fixed, perfect. So I can call to fixed and say I want it to always have 2 decimal places. Oops, didn't like that. Do I have to wrap that in parentheses? I feel like that's a console log quirk. There we go. So the idea there is that we should be able to do something like that just as easily as we could do that. The same thing, because if the result of this function call, if what it returns is the number 4, we could just swap it out for the thing that it returns. And so that's why, if you've ever seen me do those long-ass functional chains, you can save them all to variables first and then work off of the variables, but you don't have to, because if the expression evaluates to something, it's just like you were working with that thing itself.
So can you clarify how that's different from a pure function? Like definitionally, like what is the distinction there?
Sure. So referential transparency has to do with any expression. So it could be that. It could also be from the perspective of the programming language, all three of those are exactly the same. Because the expressions are referentially transparent with their values, including a function invocation. So you could say that referential transparency is a quality of a pure function, but it's not strictly a pure function. You can do things that are referentially transparent that aren't pure functions, and you can do pure functions. Every pure function is referentially transparent, but it also has some other qualities.
So what if, like in JavaScript, right, if we're doing DOM manipulation, how would functional programming work that way when we're writing functions?
So now we can go back to mod 2 when all of you are like, how come I can't just do everything in a for each? Well, you totally can. But if I wanted to do it pure, let's say I have a list of dogs. I want to turn them into a list of dog elements. So I do something like dogs.map takes in a dog. Come on, wake up, wake up. Come on now. Document's just been saved. Oh, open board. Why can't I get a fucking whiteboard tool that does what I want it to do? Great, and it shit out on me too. And did it lose everything I just did? Maybe. Yes, it did. All right, hope everybody remembers what their assignment was. So the idea is that if I do dogs.map, takes in a dog, and then does something like li is document.create element li li.text content equals dog.name return li. And then I had you guys do something like for each off of that. Okay, so why don't I just move all of this shit into the for each, and now I only need to do one enumerable. The reason why is I've taken out the impure part of it and put it in the thing that's for impure shit, and kept the pure part of this completely separate. Now I can test this pure part all by itself. That's easy. I have some confidence that this does exactly what I think it does and nothing else. And I stripped out the impure part, which is changing this variable that's outside of the scope of all of this. And like that also writes it to the screen. That's also like an impure action. You basically want to take all of those impure actions and group them all together and push them to the very end. That's a big idea in functional programming.
So in the case of JavaScript and DOM, specifically DOM manipulation, we can never completely pure functional programming because we're always doing something at the end of the day, right?
So there's a joke in functional programming that the perfect functional program would never run because its state would change from stopped to running. And we want to be disciplined about our state. So at some point, a state change needs to happen. At some point, you need to have a side effect. If you don't have side effects, you don't have a program. What we can do is push all of those side effects to as late as possible. We want to do as much of the transformations with pure functions and then push that side effect to the very end.
So it's aspirational. It's something
Yes.
to strive toward.
Exactly. And in pure functional languages, like causing a side effect is difficult to do. You need to be very intentional. JavaScript, super easy. You just use some variable that's not in your scope. That's not as easy to do in a functional language. Cool. Onward. Derek, what did you have?
I had type systems.
Cool. What are type systems about?
Typing your data, basically. So from what I saw, there's basically static and dynamic, and then strong and weak sort of flavors of those. So like weak, just like it has like super, it's like allows you to type something but doesn't remember anything about it. So unless like you were the person that just programmed it and determined what type something was, you have no fucking clue. So that's
it's determined by use. So if you use it like a number, it gets used like a number. If you use it like a string, it gets used like a string.
Okay.
It's totally contextual. Keep going.
Then there are things like JavaScript and Ruby, which I guess that's sort of how I understood those, that was like more dynamic, that like you set the type and then it just kind of took care of everything else for you.
So yeah, Ruby is statically typed, JavaScript is dynamically typed. Both of them are weakly typed.
Okay.
Did you come across anything about like the systems-y part of it and like making your own types and any of that sort of stuff?
No.
All right, so let's chat about that real quick. Thank you for sharing, Derek. The systems part of the types really becomes powerful when we start talking about our own custom types, not just strings and booleans and objects and that kind of thing. If you can have a type that's like dog or student or window or whatever, then you can start defining like mathematical operations that you can take on those, and things that you can take on subtypes of those, and things that you can take on super types of those. So that's type systems. JavaScript has Garbo typing. TypeScript's type system is very good. Even like as far as type systems go, TypeScript is fucking up there. Versus like Java, C#, C++, all of those are strongly statically typed languages, but they are not quite as nice to work with and like the custom defined type sense. Cool. Michael Navoy, what did you have?
I had recursion.
Ooh, what's recursion?
So recursion is like a substitute technique for looping. So instead of like a loop, setting a counter and then doing something as many times as the counter or subtracting from the counter, our function calls itself with like a reduced parameter. So like if we have a function that is a for loop and it adds, like we pass in 5 and it adds 5 plus 4 plus 3 plus 2 plus 1. If we pass in 5 to a function that uses recursion, it's going to call the function on 5, then part of the function is going to be calling the function on 4, which then calls the function on 3, which then calls the function on 2 and on 1. until you would reach like some specified, probably 0, and it would break the recursion. And all of this is to reduce side effects when looping, and to not require setting and maintaining state.
Beautiful. Very well put, Michael. So here's what that looks like. So we make a function called SumSequence, takes in a number like 5, and we want to add 5 plus 4 plus 3 plus 2 plus 1. So the way that we do this is we have some kind of test to find out when we're done. This is called a base condition. So we say something like, if number equals 1, return number. So if you just give us 1, it goes, all right, is 1 the number? All right, it is, cool, here's 1. Otherwise, what we do is you return a call to that same thing. You're going to return number plus SumSequence number minus 1. So the first time through, we pass in 3. Is it 1? It's not. All right, well, return 3 plus SumSequence with 2. And it goes, cool, is 2 1? No. All right, return that plus SumSequence 1. So you go, cool, is the number 1? Yeah, it is. And then a process called trampolining happens, where this entire like inception of function calls resolves. Because now it's 1 plus 2 plus 3 all the way back up through those calls. That's recursion. You have a base case, something that stops this from just running forever. And you have some part of the work that's being done in each one. And then you have something that's getting smaller, or something that's moving toward the base case every time. 3 parts of a recursive function. Ultimately, it's an alternative to looping. Anything you can do with recursion, you can do with loops. Anything with loops, you can do with recursion. But functional languages don't have for loops. They don't have while loops. They don't have if statements, technically. They don't have variables. So this is how we solve iteration kinds of problems without using iteration. Cool.
Question on that.
Yeah.
When you do have iteration at your disposal, is this a better, worse, or neutral way?
Great question. There are some things like this, or anything with like summing a Fibonacci sequence, that tends to work a little bit cleaner with recursion. It just reads easier. But by and large, you're trading memory for computation. So recursive functions are very easy on memory. They're very difficult on computation. So you're going easy on your RAM and you're going hard on your CPU. Iteration's the other way around. So there might be situations where you choose one or the other. Another consideration with recursion is, imagine I do this sum sequence, works with 10, works with 100, works with 1,000,000, works with 1,000,000,000. Can anybody see the problem when the number gets really big that we're going to run into? With this inception of calls.
It's going to be like 1 billion calls.
Yeah.
Oh.
Somebody had it.
Stack Overflow.
Stack Overflow. Each one of these function calls gets thrown onto a stack. At some point, you run out of space on the stack and get a Stack Overflow. So that's always a risk when you're using recursion. is that you might blow your stack if it has to recurse too many times. Cool. Ben, what'd you look up?
I looked up modularity.
All right.
Really, like, to the best of my knowledge, the core conceit of a lot of this being the separation of functionality into independent, interchangeable modules. A module has a single responsibility, kind of a concept that I think we've all gotten pretty familiar with, even if we didn't have a name for it. So really, actually something that Amy brought up this morning, the idea of getting away from having a monolithic application, and instead having several smaller components that work toward the whole. Module as a word has pretty different meanings across multiple languages, so I'd be dubious about when you see it. It can mean anything from a single thing to a package of things. Notable folks using it: C#, Dart, Java, MATLAB, Perl, Python, Ruby, JavaScript. Yeah, separation of concerns. I think that's like the core concept.
Cool. One other thing I would add in the context of functional programming: separating behavior from data. This is the opposite of OOP. OOP, we keep our methods and the properties that are that the methods are acting on in the exact same place. We want all of those, what a dog is and what a dog can do, those move together in one object. That's the whole point of OOP. FP, this is maybe one of the biggest differences between them, is we're keeping those two fucking things as far away as possible. We want to describe the behavior as abstractly as possible, nothing to do with the data. And a great example of that is right here. So if we take a look at what this really is, think about this more abstractly. It makes an element, it sets a property of the element to some property of the thing that we passed in, and then it returns this thing. You can imagine taking that, like abstracting that out a couple steps, and we end up making that a function that takes in the type of element that we want to make, the property of that element that we're setting, and the property of the object that we're going to rip out and assign to that thing. And at that point, it doesn't matter what data you pass into it. We've abstractly described the transformation that's occurring there, especially when you combine it with something like a map. You have an abstract behavior. That's what we're going for with functional programming, is trying to figure out what all these abstract behaviors are, and then the data doesn't matter. We just plug the data in and it does the transformation. Very nice. Sam Evans, what you got?
So I had declarative functionality, I guess.
Declarative approach.
Declarative approach. So the meat of this is mainly the difference between declarative and imperative programming. In imperative programming, the focus is on like what you're actually doing. So it was kind of harps back to everything we've been talking about, where like in an imperative code, you write like a for loop that does all this stuff, right, and has all these side effects and things. And in declarative code, you just call another function that does that somewhere else, and you don't really care how it does it, but you care what return you get, which is, I think, a little bit silly, because somewhere something is happening to that, but the idea is that you don't care. Like,
correct,
is you want to use, like, sort of like in Ruby or JavaScript, you would favor built-in functions over like doing it yourself with the for loop, because all you care about is the return, and that's what you're going to work with. And then that function you're calling has all of these other properties we've been talking about, or supposed to.
You can say wrap up imperative behavior in functions. Cool, great description. So, por ejemplo, we can do stuff with imperative loops. So we have some imperative loop here, and maybe for each of these, we're taking the array, and we have this transformed thing, and we take the array, and we do like transformed dot push array at I. Dot some property. All right, so that would be the imperative way to do that. We're telling the computer how to do this job. You're going to initialize a counter. Then you're going to check this condition. Then you're going to look up this array.I. Then you're going to look up its some property, and then you're going to push it onto this array. We're getting real down to the metal and telling the computer how to do its job. And to Sam's point, at some point, somebody needs to do that. The computer is not going to figure out how to do it on its own. Now here's the rub. There's like 6 different places you can fuck up this code. We can make this an J instead of an I. Happens all the time when you're working with nested loops. You could, is it less than array.length? Is it less than or equal to array.length? I know sometimes there's a -1 involved with this. Is it plus plus or minus minus? A lot of the times you want to start at the end and work your way down to 0. What happens if transformed isn't already an array and I try to call push on it? That's going to throw an error. What if some property doesn't exist on this? So many places that this can break. If I have that wrapped up in a function that I've bulletproof tested for all of the different ways that you can do a transformation, like for example, if I can do something like const transformed equals, and I'm going to show you, like, I know this isn't the JavaScript way of doing it, this is the functional way of doing it though. There you go. That's what that would look like with Lodash. Where's the room for error? There's no daylight showing that you could fuck up. And in addition to that, if you know what these words mean, I've also, like, as succinctly as possible described the thing that I want done. I have declared what I want done. This, I don't care how good a programmer you are, you got to stare at that for a second to figure out what it's doing. You need to work backward to what the intention is. You don't with this. That's declarative programming. Cool. Gordo, what'd you get?
Higher order functions.
Beautiful. What's a higher order function?
Higher order function is a function that either takes in one or more functions as arguments or returns a function as its result.
Or?
I'm sorry?
Or?
Returns a function as its result.
Or both.
Or both, yeah. Examples being like a .map, .filter, .reduce.
Absolutely.
Best advantages, or biggest advantages, I guess, are just the greater reusability. So you're not having to write those for loops, those iterations every single time. So.
Great explanation. So, for example, if we take a look at this dog mapping thing that I had over here, let's say that I did the super abstract version of this, where it's a function that takes in what kind of element you want to make, takes in what kind of property you're setting, takes in the property you're calling on the thing. Now I have this really abstract piece of behavior that I can test the shit out of, that I can get really confident in. And when I reuse that, it works exactly the same everywhere in my application. That's really efficient code. Also, like, it's pretty critical to how JavaScript works overall. If we think about things like event handlers, that's a higher order function. You think about how .then works, we pass a function into that, that's a higher order function. Or the thing that Haley Ringer figured out yesterday, this is the other side of this. Actually, I'm gonna put this over here. We can return functions also. So we could say something like const sum result equals so this is a chain of functions that return other functions. So we're saying there's this function that takes in a parameter called C and then returns the string sum result. That's just regular fat arrow function stuff, right? Okay, well, what if that function was the return value of a function that took in a parameter called B? And what if that function was the return value of something that took in A? And then you assign the result of that. So like a really common use for that in functional programming is, this is like sort of related to pure functions, but ideally your functions all take in exactly one argument. But let's say you needed 3 different things. Well, then what you do is like have functions that return other functions. So in practice, that would be something like sum result equals sum result 3, 4, 9. And that's called currying. If you want a more practical example of that, I wrote a blog post called How Closures Work. Talk more about closures next week, but your practical example would be using a map where you need access to more than one variable. So it'd work like this. You want all of a particular user's favorite Pokemon. So user has like a favorites array. And if we want to like use that in say a filter, we could say, all right, I want to build this function that returns another function. And now it has access to both of these variables, even though each function only took in one argument. It's kind of a heady concept and not a very good one for a Friday. We'll talk about it more next week, but that's the TLDR on higher order functions. Cool. Thank you, Brian. Haley, what'd you have?
I had first class functions, which are functions are treated like a variable, meaning that they can be passed as an argument to other functions. They can be returned by a function, and they can be assigned to a value. And just an example of first class function language, which is functional programming, is Haskell or Scala. Mm-hmm. And JavaScript's a scripting language that has first class functions. So like, I thought that distinction was interesting.
Excellent. Thank you very much. So well put. And as you might imagine, very closely related to higher order functions. Higher order functions specifically refer to passing things in and returning them. The like extra thing that a first class function can be is just assigned to a variable. It's just a regular old value. And I'll call out that we can't do that in Ruby. Ruby doesn't have first-class functions. Basically, no object-oriented language does. You couldn't have a standalone method that you assigned to a variable. That wouldn't make any sense. We can do that all the time in JavaScript because JavaScript has first-class functions. Cool, very nice. Thank you, Haley. B-Rad, what'd you get?
I did discipline, so discipline state. It's essentially kind of interrelated to pure functions in a sense of like trying to avoid bugs through encapsulating the state within the function, because you don't want to modify the external state, and it's just to avoid disorder and entanglement. But yeah, it's essentially it.
Good, very nice. State is variables. Like,
Okay.
that's it. Properties on objects, variables in JavaScript, that's state. If we're being disciplined about it, then we can do things like this, where we're making a variable here. It's technically state. It exists for exactly 3 lines, and then it goes away. That's being disciplined. Having as little state as possible. Now, if li was defined way out here or in another module or in 3 different fucking places, now we're not being disciplined about state. Now state can be set from anywhere, it can be read from anywhere. That's a no-no in functional programming. If you're going to use state, be responsible with it. Keep it as locked up as possible. Cool, very nice. Brooke, what'd you find?
I did immutability, and the only thing that I can say is immutability is the core of a functional programming. It makes things very simpler, makes things a lot more readable. It's like writing a program, but with the inspiration of like a writing poem. You know, you can, like, every line is kind of, you know, powerful, but like not duplicatable. What else? Yeah, once you set a value, you can't change it, basically. And that kind of actually takes away the leverage, or not leverage, the incident of you actually making mistakes, you know. Once, for example, if you say y equals x squared minus 1, you can't go back and say x equals x squared minus 1, because you already set the value x squared minus 1 to y. So there's that notion of it.
Good, very nice.
Yeah, that's what I got.
Very good. So the main idea behind immutability is once you set a value, can't change it. And this is borrowed from math. So yeah, if I say x equals 2, if I say that in an equation, and then later in the equation I say x equals 5, now we've like violated one of the, I think literally the oldest piece of logic in the world, which is A has to equal A. A can't equal not A. So if x is 2, x can't also be 5. Like, that's basic logic, right? Now, in the 50s, there was this thing developed called the von Neumann style of programming, which is basically what all of us do most of the time now, where x is just some kind of placeholder. It's just a bucket. We can add stuff to it. We can take stuff out of it. We can change the things that are in there. But this creates all kinds of problems, because if I'm relying on x, and x can be any number of different things, now my programs need to be able to account for that. So in practice, this ends up looking a lot like this. Instead of going, let something equal 2, and then something equal 2 times something, and then something equals 5 divided by something, then we just give these different names. So that something never changes. That another thing never changes. And yet another thing never changes. So we've gone from mutable data to immutable data. Once these things get assigned, they don't change. That's the big idea.
So when is it appropriate to use a let? I know we basically said always use const unless you have a good reason not to.
Correct.
Because let would not be, it would be mutable in most situations.
Correct. Yeah, let is always mutable. Now the funny thing is that const isn't immutable. Const is blocked from reassignment, which is like halfway there. Basically, it has to do with objects. So if I do const like that, I can still do something dot new property equals that. That's not immutable. I super mutated it. I can also do like make an array and then do some list dot push. That's not immutable. So it's close. It's almost like that. But yeah, let is always mutable. And so in functional programming, there's no place for let. Tons of place for that in object-oriented programming. Tons of place for that for procedural programming. But one of the reasons we tell you to default to const is if you want to do a reassignment to something and you have const, it'll throw an error going, whoa, 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 that's a const. You can't reassign that. And you go, no, never mind, it's cool. And then you can change it to a let. If we think of that the other way around, if something's a let and we don't want it to be a reassigned and we accidentally do it, you don't get a warning. You don't get an error. You have no clue that that happened. So in general, always go with the most restrictive thing you can so that it'll yell at you when you break the rules. And if you go, nope, that's cool, I want to break that rule, you get the choice to do that then. Cool, very nice. So all of these things together form the core of functional programming. If you guys want to, we can talk more about this next week. We can do a little bit of practice with it. But really, if you just have like a grasp of some of these ideas, that's probably like an okay place for a code school student to be. If this is like awakened something in you, like there's more and it's awesome. It is so fucking fun. But in general, functional programming and object-oriented programming are mathematical versus literary approaches to programming. Functional programming is a lot like math. Object-oriented programming, we're talking about nouns and how they verb each other. That's very literate. There's places for both of those. Basically, any kind of pure data transformation, functional programming is the toolbox I reach for every time. If it's something that is best modeled as like a real world kind of thing, OOP is not a bad thing to reach for. And with something like JavaScript, we get to kind of get the best of both worlds. You can just seamlessly jump back and forth between them. Cool. Any last questions?
Kyle, I just slacked you one because I didn't know how to like explain what I was trying to ask without actually like sending you the code.
Okay. So the thing that Sam sent me was like a variety of things that were either using Boolean logic or ternaries. and no difference from the perspective of functional programming. Those are identical.
For everyone else, I was asking, basically I was trying to turn a large if-else statement into functional programming with higher.
I see what you're saying. No, like that doesn't really change it at all either. One of the things we can talk about next week is dictionary dispatch and dictionary lookup and dynamic dispatch, which are the ways that you get rid of if statements in functional programming.
So a dictionary lookup would be better than doing what I sent you?
Yes, much. Because the thing you sent me isn't actually a lower cyclomatic complexity. Dictionary lookup would be.
Gotcha. Okay, thank you.
All right, so objective with this was that you would be able to recall 3 different tenets of functional programming. So I would like you to Slack me at least 3 different things that you took out of this lesson. Go.
And before we all jump off here, I'm just going to put it on the record that I will try to remember to ask for this next week. It would definitely be helpful for me if we had another lesson to just kind of sit with this stuff to get it to sink in. So anybody else feel free to ask for it too if I forget.
You're beautiful.
I'm geeking out. I'll remember
things to talk about in programming. So. Slack me 3 takeaways. All right, just need a couple more. All right, just need 2 more. Cool. If you're writing me something, finish it up. Otherwise, enjoy lunch and learn. And what am I clapping for? Something in the fucking day. Have a good lunch. Elsewise, cheers.